Greetings and welcome. In this session, we are going to discuss numerical on Venturimeter. In the last video session, we have discussed about the construction and working principle and key parameters of Venturimeter, which is used to measure the discharge passing through a pipeline in industrial applications. So in these video sessions, we are going to see a numerical to calculate discharge and pressure difference between inlet and throat of Venturimeter. So let us see statement of the numerical. Statement is like a 300 mm by 150 mm Venturimeter is provided. Now here first dimension is of pipe diameter 300 mm and second dimension is of throat diameter, that is 150 mm. This is in a vertical manner. Now it carries oil of specific gravity 0.9 and flow is being upward. So direction of flow is given in upward. Difference in elevation of the throat section and entrance section of the Venturimeter is 300 mm. Now this we will see in a detail in a diagram. The differential U2 mercury manometer shows a gauge deflection of 250 mm. So here in the Venturimeter we know that U2 manometer is used to measure the pressure difference. So here deflection, that is a Y, given in the form of mercury, and that is about 250 mm. Then coefficient of meter means Venturimeter is given here as a 0.98 and specific gravity of mercury we have to take as a 13.6. Here it is asked to calculate two parameters. First is the discharge of oil and second the pressure difference between the entrance section and throat section. Now for this we will have diagram. So here this is a diagram of vertical Venturimeter as per the given data. Here this is a pipe inlet and this is a pipe outlet. Between these two ends this is a Venturimeter fitted. It has three parts. First part is a converging cone, then throat, and then diverging cone. So here the difference between elevation of entrance pipe section, that is a 1, and throat section, that is a 2, that this difference in elevation is given as a 300 mm. Means Z2 minus Z1 we have to take 300 mm, means 0.3 meter. Then pipe diameter is a given 300 mm. So D1 in a meter for the calculation we take as a 0.3 meter. Throat diameter is given in mm, that also we take in meter, 0.15 meter. Flowing fluid through this pipe is a given oil. Its specific gravity is 0.9. Manometer, the fluid which is used, that is a mercury. Its specific gravity is 13.6 sm. And flowing fluid specific gravity SL. L for liquid. SL, specific gravity of liquid passing through the pipe, and M for manometer, fluid in a manometer, specific gravity of fluid in a manometer, that is SM. Then here coefficient of discharge for the Venturimeter, that is CD, 0.98. So here now we will first of all find the areas of the pipe and throat. So here we see first of all areas. Pipe area is calculated with the help of formula. A1 is equal to pi by 4 D1 square. Diameter is 0.3 square. Doing the calculation we find the area in meter square. Similarly throat area, by putting the value of diameter D2 in the formula we find value in meter square. Then we calculate Venturimeter H. For that, as per the discussion, formula for SM, manometric fluid, which is mercury, as it is heavier than the fluid oil passing through the pipeline. Thus we use H is equal to Y into SM by SL minus 1, where Y is a deflection of Venturimeter, a manometric fluid deflection, that is given 250 mm. In a meter we take 0.25. Specific gravity of mercury in the manometer 13.6. Specific gravity of oil in the pipe SL 0.9 minus 1. Doing the calculation, we find Venturimeter head in a meter. Then we use theoretical discharge formula. QTH is equal to areas, pipe area A1, throat area A2, square root of 2GH divided by inside the square root A1 square minus A2 square. Putting the value of this A1, A2 area here, 2 inside this square root 2 multiplied by acceleration due to gravity, that is a G 9.81, and a calculated value of Venturimeter head in a meter that we put here. At the denominator, putting the areas values here as per the formula. Doing this calculation, we find theoretical discharge in meter cube per second. Actual discharge is calculated by using the relation, that is a coefficient of discharge multiplied by theoretical discharge. Coefficient of discharge for the Venturimeter is given 0.98 multiplied by this calculated value of theoretical discharge. So finally we find here actual discharge of the oil in meter cube per second. This was the first part calculation, that is a discharge of oil. Second part of the calculation, that is pressure difference between entrance and throat section. So for that purpose we use Bernoulli's equation. So applying Bernoulli's equation between the two sections of the pipe, that is the section 1, that is a pipe, and section 2, that is throat. So here this equation we write P1 by W plus V1 square by 2G plus Z1. These are the three energies: pressure energy, kinetic energy, and datumenergy, which are for the pipe inlet. Similarly, these are the energies at throat section: P2 by W plus V2 square by 2G plus Z2. As we consider this for ideal fluid, means we don't consider here losses. So neglecting losses, we use this equation. Now, this equation we arrange in the form P1 by W plus Z1 we take together minus P2 by W plus Z2 together. So these are the two brackets, and the parameter of velocity, means this is a kinetic energy at the inlet. This parameter we take on the right side of the equation. That is why it becomes here V2 square minus V1 square divided by 2G. This 2G we take common for the both. We write common for the both at the denominator. So this right hand side, V2 square minus V1 square by V1 square divided by 2G. This is taken as a H. So this H is called as Venturimeter head. Left side we write again arrangement of these terms. Pressure terms we take together, P1 minus P2 divided by specific weight of the oil minus this minus sign, and inside the bracket, that is why Z2 minus Z1 comes. Now this Z2 minus Z1 is a elevation difference. That is what we have seen in a last diagram, that is here 2 and 1, this difference Z2 minus Z1 0.3. So that's what we use in the, so Z2 minus Z1 0.3 meter, and H we have calculated, that is a head, by using the formula. So that for value what we have got, that is written here. Now this value we put in this formula. H we put here, Z2 minus Z1 we put here. W means specific weight of the oil. Specific weight of the oil we have to calculate. We use the fluid mechanics first chapter, that is a fluid properties. There is a relation, that is specific weight of any fluid is equal to specific gravity of that fluid multiplied by specific gravity into 9810. That is a specific weight of standard fluid, that is water. Now here we take this in Newton per meter cube because all the dimensions what we have taken here, these are in the form of meter and Newton, because finally we are getting the value of pressure in a Pascal, that is Newton per meter square. So W of oil is equal to specific gravity of oil multiplied by specific weight of water, 9810 Newton per meter cube. Product of these two, what we get here, Newton per meter cube, that is specific weight of oil. So this specific weight of oil we put here, P1 minus P2 divided by, and these are the remaining terms as it is. Now in this, P1 minus P2 is unknown. By doing the calculation of this equation, P1 minus P2, we get the value in Newton per meter square. This is what pressure difference between entrance and throat section. So as a summary part of this numerical, we found the solution for this numerical in two parts. First is a calculation of discharge. So for that purpose, we have calculated first of all theoretical discharge. After that, by using CD value, we calculated actual discharge. In a second part, to calculate the pressure difference by using Bernoulli's equation, we got the value of P1 minus P2. That is between entrance section and throat section. Let us meet in the next video session. Thank you.